Okay. So today we're going to continue though. Yesterday we did intervals. So next natural process will be what? Tests. Okay. So we're going to dive right into the testing side of things. Again, there really isn't much for me to go over though, because isn't it literally the same as what we've been doing? Just now 2 samples instead of 1 sample, which you've already seen for proportions. So you kind of already know how this is going to go. All right. So, does breastfeeding weaken bones? Breastfeeding mothers secrete calcium into their milk. Some of the calcium may come from their bones, so mothers may lose bone material. Researchers compared a random sample of 47 breastfeeding women with a random sample of 22 women of similar age who were neither pregnant nor lactating. They measured the percent change in the bone mineral content (BMC) of the women's spines over 3 months. Comparative Bach plots and summary statistics for the data from Fathom are shown below. Based on the graph and numerical summaries, write a few sentences comparing the percent changes in BMC for the two groups. So we're comparing two distributions. What pieces do we compare? Socks. All right, and again, cool thing is you have graphical displays already to guide that conversation. All right, so here breastfeeding mothers have a lower mean mineral content with more variability than other mothers. Both distributions appear slightly skewed right without outliers. So again, just talk about socks. All right, compare the elements of socks. And again, remember, when you're making comparisons, you don't need to give numerical values. You can just make the comparison, okay? You can just say which one is greater, which one is smaller. Yeah, yeah.
Oh wait, never mind. I think I answered my question. I was gonna ask, when do you use the 1 sample difference and the 2 sample difference? I'm guessing it's when you have.
That's when it's matched pairs, which we'll actually get to. I'll talk about that tomorrow. I've got you. All right. B. Does this data provide convincing evidence? What does that tell us to do? A test. All right. Now, in this case, what name would be appropriate for this test? I assume you can get there, even though we've never seen it before.
Test for a difference in means.
Oh, look at you guys. You're wonderful. Two-symbol t-test for a difference of means. And then, of course, what comes after our state step? Plan. All right. So, oh, thank you. That was almost a rookie mistake of me. Thank you. All right, hypotheses. Oh my God, I can't believe I forgot that. What is wrong with me? So, hypotheses. So remember, the null always uses an equal sign, right? Now, in this case, what is equaling? The two means to each other. Now, if we're doing means, though, this isn't going to be P. What's it going to be? Mu. Okay, so we're going to say mu of breastfeeding equals mu of non-breastfeeding. And then what do we think is happening? What did they say could be happening because of breastfeeding? They're losing bone mass. So wouldn't we angle it as less than, right? We think breastfeeding mothers might be losing some calcium in their bones. All right, now I'm ready to move on. All right, plan step. Did they mention randomness? I think so too. I hope so. If they didn't, we're in trouble, guys. Random samples. Love it. So glad glad you have a different drink this time, so I don't accidentally try to take it.
These things are nasty, gosh. I'm just so tired. I don't like them.
They're delicious. It's orange. Of course it's great.
Not feeling it. I'm so tired, gosh.
All right, normal. For normality. For proportions, okay, proportions we look for successes and failures. What do you care about for means? Sample size being at least 30. It's not. You're right. But don't worry, I'm not that mean. Because what's here in its place? Even though the sample sizes are too small, they already graphed it for us, right? So they saved us the trouble. Obviously, if they give us the graph, you don't have to do it yourself. But what I would say is neither sample size is at least 30. However, the given box plots of the sample data don't show heavy skewness or outliers.
How often on the AP test did we have to like graph?
Ooh, that's a good question. I'll actually look today during prep because now I'm actually curious how often they make you do it. I feel like not often because they probably don't want to look at it either, just like I don't want to look at it. But yeah, I'll actually go back and look to see how many times they've actually done that. I want to say more often than not, they either give you the display or they give you a big enough sample size. But I will look into that because that's a really great question. Oh, wait. One of them was over 30? Oh, it was. One of them was 47. Oh, well, that's silly of me. All right, so one of them was actually good. I should really start paying more attention. Right.
Not like that's not hard.
Okay, deal. All right, independence. What do we look for when we're sampling and we need independence? Less than 10%, yeah. So both of these samples are less than 10% of their respective populations, meaning breastfeeding versus not pregnant. And then we always want to state that the samples are independent from each other as well. Yes. What? I did not bring. I brought M&Ms instead. Oh, I should have saved some of that apple pie M&Ms from. Yeah. There's pumpkin pie M&Ms. I should have planned ahead and saved those from Halloween.
Those aren't good.
Oh.
If you had to say them from Halloween, probably not.
M&Ms don't really go bad. They're chocolate.
That's what they tell you.
M&Ms are.
I thought Dr. Pepper didn't go bad, and I took a sip out of Dr. Pepper that was on my bedstand for a long time. It goes bad.
Had it been opened?
Yeah.
Well, there's your problem.
It all like separates.
If you-
It does not taste good.
But kiddo, if you hadn't opened it, would have been fine.
Oh, I just
Tasted like-
understand your shirt.
Rotten.
It says pie.
Yeah.
I get it now. I didn't know what it said.
All right. Do step. So the do step nowadays, isn't it really just determining what the right program is? Isn't that really all that we need? So let's think about it. This is not a proportion, so we know it should not say proportion. It is a t-test, and there should be a 2. Which one? But I think you said 4. Does number 4, do we agree? Does 4 sound good to us? It does sound great. Were we given raw data or some summary statistics? Some summary statistics. All right. So the breastfeeding mothers had negative 3.58723 with standard deviation 2.50561. Sample size was 47. Other one 0.309091. 29832, and there were only 22 people. We think it should be smaller than. Oh, whoops. Smaller than. Do we ever change this pool thing? Nope, never. Just don't touch it. Pretend it's not a thing. Oh, geez. Look at that ridiculously small p-value. Like crazy small p-value. We are going to reject that. So you want your t-test statistic, you want that ridiculously small p-value, and you want your degree of freedom because it's a t. And I think someone already said it. What conclusion are we going to do with that really, really, really tiny p-value? We're going to reject it hard.
It's garbage.
Right. Yep. So, here's the values. And then since the p-value is way less than, like, basically 0, way less than 0.5, we reject the null. That means there is convincing evidence, yes.
Oh, I was just wondering, how do you get like that degree of freedom? Because isn't it just 1 minus the?
But because there's two samples that we're blending together, it's actually a formula that they've deemed as more complicated than you need to know. So there's two things you can do. You can use what the calculator says, or what we call the conservative degree of freedom is where you take the smaller sample size and take 1 from
I
that.
just wanted to know how you got it.
I will find that formula for you and show you just why you don't want to know it.
I think I looked it up once.
Okay. No, it's actually terrible. So yeah, so they deem that formula as just above a high school level. So that's why they're like, we don't care. Just either.
College level.
Yes.
So it's above a college level.
Sure.
Okay.
All right. So we still want to keep in our conversation type 1 and type 2 errors. Okay, those aren't going to go away just because I think the more we practice it, we want to keep up on that skill. So describe a type 1 and type 2 error in the context of this setting. Generically, remind me, what's a type 1? Rejecting when you shouldn't have. Okay, so wouldn't that say we found our evidence when we weren't supposed to? Right? So concluding there is evidence, but there really isn't. And then what's type 2 again, generically?
Type 2 is you didn't find evidence, but you should.
Yes, when you fail to reject what you should have rejected. You don't find the evidence when you should have. All right. So, next example. Poisoning by the pesticide DDT causes convulsions in humans and other mammals. Researchers don't know what's going on there, work to understand how the convulsions are caused. In a randomized comparative experiment, they compared 6 white rats poisoned with DDT with the control group of 6 unpoisoned rats. Electrical measurements of nerve activity are the main clue to the nature of DDT poisoning. When a nerve is stimulated, its electrical response shows a sharp spike followed by a much smaller second spike. The researchers measured the height of the second spike as a percent of the first spike when a nerve in the rat's leg was stimulated. Further results were, and then here is the control data. So here's the ones that had DDT, and here's the control group. All right? Computer output for a two-sample t-test on these data from SAS software is shown below. Note that SAS software uses two-sided p-values. Okay? So, do these data provide convincing evidence that DDT affects the mean height of the second spike of electrical response? Carry out a significance test to help answer this question. All right. So, what are we going to call this process? Yes, two-sample t-test for a difference of means. All right, then I won't forget this time. We need hypotheses. So remember, we need meaningful labels, right? Meaningful subscripts. What would be a good way to differentiate our two groups here? Well, using mu, yes, but what subscripts could work for these two groups? Control, not control, maybe DDT and control. Again, you can do what you want. You just have to choose subscripts that meaningfully differentiate the groups, okay? So one of them had a DDT poisoning, the others were a control, all right? Now notice the phrasing here. They just want to know if it affects the mean height. Did they say how they think it could affect it, what direction? If they don't establish a direction, what do we do for the alternative? If we don't know which way it could go either way, to be honest. Not equal to, yeah. All right, how did they discuss randomness here? What did they say about that? Yes, they called this a randomized comparative experiment. So basically what that means in more common language is they randomly assigned these rats to a treatment group. All right, normality. Yeah, it's not big enough, is it? Neither one. So we do need to graph this, okay? I'm trying to remember what graph I have on here. Oh, dot plots. Good, because that's usually easiest anyway. Um, so if you whip up a quick dot plot comparing these two, okay, so you do need to separate them. So here's a control group, here's a DDT group, but you do have to separate those, okay? Give kind of a graph for each one because you have two separate groups. And then what do we want to say about these two groups? Yes, there's not major skewness and neither has outliers. Independence. So here, this was an experiment, wasn't it? We didn't talk about random sampling. This was an experiment. How do we adjust independence for experiments? It's the randomness, yeah. If you're not sampling, you don't care about the 10% condition. It's the randomness here that is helping create the independence. All right, and do step. So again, the big piece of the do step is finding the right program, because I think you're getting a sense now with all the programs we're using. It is important to know when to use each one, right? Because we're on what, our eighth, I think. We're on our eighth program now, so it is very important to know how to use each one, when to use each one. Okay. So which one are we using today? 4. Yep, it should not say proportion, okay, because it's not for proportions. It is a t-test, and there were 2 samples. All right, again, we were given, oh, my bad. Wait a moment. Backtrack. I was getting too excited to use the calculator. I forgot about this. So let's look at this for a second, okay? So what are we looking for? When it comes to the do step, what do we want from the do step? We want the t-test statistic, we want the p-value, and then what else do we need along the way? We need degrees of freedom. All right. So do you see a spot on here that gives you that kind of information? I do. T, DF, prob. Well, isn't the p-value kind of a probability, basically? Right? So I think this is what we need. Now, the weird thing is you see there's 2 of them. That's odd, isn't it? So remember when we talked about pooled versus unpooled yesterday, and I said ignore that pooled really doesn't matter. It's not really a thing. Do you remember what I said about that? Similar standard deviations. They even comment on that, don't they? Variances. Are the variances unequal or are they equal? Well, look at these dot plots. What do you think? Is it variability? Is it similar or not similar? Way not similar, right? So which one of these feels appropriate? The unequal. Okay, so this is going to be what you want. Okay, so those are the components to put in your do step. This is the t-test statistic. This is your degrees of freedom. That is your p-value. Because do note up above, I said that this table was giving it to you as a 2-sided deal already, so that is the p-value that you want.
This degree of freedom thing is confusing. How are there gonna be different ways to get there?
I know, I know,
That just gets so
I know.
further to answer something that doesn't matter.
You're not wrong. All right. So jot all that down. Beautiful. What conclusion would we draw then?
Reject.
Oh, we'd reject again. Wait, what? Whoops, I forgot to wipe that out. Because remember when I said copy paste? I literally did that. Oh, whoopsie.
Wasn't even a question of proof, so there is I'll do that. I'll do copy it actually word for word.
Like
That would be great.
actually copy paste like paste it and then mess it up.
If you want, if to get me my score, you need to do a significance test. What if to get your score, you had to like calculate it? Like they gave you like a bunch of stats, and you had to calculate your probability of
Getting a certain score.
Yeah.
Interesting.
That'd be awesome.
Actually, it's really fun. They actually do give a distribution each year after grading. They give a distribution of what percent nationwide got each score. So I could do some, I should do some probability with that. Oh my God, I'm missing out. I should be looking at that.
No, like if you find a note that you got like way higher.
Oh God. And you don't even get your score if you can't figure it out. All right. So what if we had made a 95% confidence interval, right? This was a two-sided test, so it makes sense we could compare it to its interval counterpart. Okay, we ran a 5% test, so let's compare that to a 95% interval. So note, we rejected the null. Doesn't that mean we reject the idea that these could be the same? Right? We reject the idea that these are the same, that there's no difference. We legitimately believe there is a difference, right? Everybody on that same page? So if we legitimately believe that there is a difference, would it make sense for 0 to be in the interval? No. Okay? So here, we don't think 0 belongs there because we don't believe that it's possible to have no difference.
Like, are you in the 95% of people who got threes?
All right. No, actually, I did put some things in here that are important, and it's not the full thing anyway. So we do actually have to do it. I'm sorry. Um, what?
Is it gonna fail?
I don't know.
It's not the full story. It's not the four-step process.
Let's see. John wants to compare the costs of one and two bedroom apartments in the area of his college campus. He collects data on a random sample of 10 advertisements of each type. The table below shows the rents in dollars per month of the selected apartments. John wonders if two bedroom apartments for rent are significantly more on average than one bedroom apartments. He decides to perform this test. Okay, either they're equal or the two bedroom is more. Name the appropriate test and show the conditions are met. Okay, so spoiler alert, doesn't that mean that they're met?
They're not. They're not.
So, name the test. Well, what are we doing today?
Two samples, t-test for t-test.
Love it. And again, we're going to check our conditions. Um, was he random about this?
Yeah.
Yes. Okay. Unfortunately, I'm sorry, twice in one day. This is actually kind of mean of me. What do we need to do? Graph. I hope I put a dot plot here. That would be lovely. Please be. Oh, good. I actually do kind of feel mean now. Two of the three examples. That's a little much. Yeah. I mean, at least this is really easy to make a dot plot of. Like when given the choice, I would always do dot plot. Unless you have to type the data into the calculator, because then you might as well just let it make a box plot for you. And then we were sampling. What do we discuss in terms of sampling? Yeah. Both samples are less than 10% of all advertisements of that type. The samples are also independent from each other.
That means all the hard work can't be worth it.
Right.
Oh, that's what I'm.
Well, because you actually asked this quite a bit.
Mm-hmm.
This is what I think you need to see.
Are you asking me to do this?
Well, no. I'm saying you've asked, will it ever fail? And I said, a very rare circumstance, like if they're just asking about conditions. So this is a really good example to show you how that could pop up.
I just want it to fail. I don't want
No,
it right here. I know it failed right here.
yes, it did fail. Well, no, I'm just saying I gave you one that you've been asking for, and then you didn't even come to my elk time for it.
So
All right, so the appropriate test yields a test statistic of negative 2.025. Calculate the p-value and interpret this p-value in context. All right, so let's think about this. So t's and z's, aren't they basically z-scores, right? And didn't we already say that this is normal-ish enough? Um, and they're asking for a probability. So when it's a z, what does it mean? How do we go from a z-score to a probability? Normal CDF, but this is a T, so what do we use instead? TCDF. Oh, you guys are wonderful. All right, TCDF. Now this one is what? I don't like that. Why isn't it taking me? There we go. Um, this one is angled downward, isn't it? Isn't this one angled negatively? So don't we want just a really negative number going up to that T-score, right? Now, degree of freedom. Remember when I said you really don't need to know much about this except in these circumstances? So, because we're not running the test, do we have that awkward calculator to degree of freedom to use in this case? No, unfortunately, we don't. Okay? So instead, we can use that next best thing. Yesterday, I talked about something called the conservative degree of freedom. And how do you find that? Yeah, the smaller sample size -1. So when you need to, that's what you put because you're not going to know how to get that other awkward one that the calculator can do for you. Okay. What were the sample sizes here? Were they both 10? All right. So we're going to put 9 here. All right. The smaller one -1. So again, just for your sake, I might jot this down so you remember where this value came from. Do I need to multiply it by 2? Because sometimes that's a thing, sometimes it's not. Do I need to multiply this? No. Why not? It's a one-tail test, right? The alternative actually has a specific direction. If it were not equal to, isn't that where we double this? Right? Oh, surprise. All right, so here's our p-value, right? Ooh, interpret the p-value. All right. How do we interpret a p-value?
Given the null is true, that's our rarity of getting.
Yep. So given that there's no difference, okay, given that there's no difference between apartment costs, there is a point, oh, what is it? Oh yeah, point zero two nine. Yeah, actually this is a little bit off, isn't it? What did you guys get? And here, I'm actually going to change this phrasing a little bit. And don't worry, I'll read this. I'm just getting my thoughts down. All right, so I'm changing this to be a little bit more clear. So where the observed mean for the two apartments, or the two-bedroom apartments, is at least this much larger than the one apartments. Okay, because here there was a direction, so you should be clear which one is bigger than the other. Okay, so again, I'll read that because I know it's just chicken scratch. I was writing really quickly. So where the mean for the two apartments is at least this much larger than the one apartments. All right. What conclusion would be drawn? You would reject the you would reject the null. Okay, and again, this one is a little bit off from what we got. What kind of error could we have made? We rejected the null. What kind of an error could that accidentally lead to? Type 1. And this is kind of what I was getting at earlier. What if the alternative had been not equal to? What would we have to do to that p-value we found a couple steps ago? Times it by 2. 0.0368 times 2, 0.0736. So again, do watch for that. I will tell you that's something that I actually got quite a few kiddos on one of my multiple choice questions that's on your upcoming test. Okay, so just a heads up, do make sure you're noting what that alternative is, because notice that could make a difference. If it had been not equal to, what would that change your conclusion to? Fail to reject. And you know if it pops up in the AP exam, you know they're going to make a difference, right? To test that you knew what you were supposed to do. Okay? So just something to pay attention to for me. Really quick, let's do a couple multiple choice, and then I will be done for the day and give you guys a couple minutes to relax. So, a researcher wished to compare the average amount of time spent on extracurricular activities by high school students in a suburban school district with that of a school district in a large city. The researcher obtained a random sample of 60 high school students in a large suburban school district and found that the mean time spent on extracurricular activities per week to be 6 hours, a standard deviation of 3. The researcher also obtained an independent simple random sample of 40 high school students in a large city school district, and found the mean time spent on extracurricular activities to be 5 hours, standard deviation 2. Suppose a researcher decides to carry out that test versus a two-sided alternative. The correct test statistic is, all right, so this is where you're probably going to want this. Okay, isn't this magic page going to show us how to set this up, right? So test statistic is your statistic minus the parameter. Well, isn't the top the same on every one of them anyway? So is the top really impacting us at all? Not really. So what we really care about is that standard deviation piece, right? Well, two sample standard deviation, that sounds like a beast. But isn't it shown right here? Right? So as long as you can follow patterns, you will be just fine. So a couple things to note. First, notice this whole thing is inside of a square root. C doesn't have any square roots whatsoever. So I don't like C at all because it doesn't have the square root that the pattern shows. The pattern also shows, the standard deviations squared, but not the sample sizes. B and E are not the same, but they're not. Hey. So isn't it B because this is a T, not a Z? Yeah. What? All right. So that test above, we got a test statistic of a p-value of 0.048. So notice every one of these is comparing that to 0.05. So first, what would our conclusion be? We would reject, okay? So right away, doesn't that rule out A, B, C? So remember, when you do reject, what is that implying?
You found evidence.
Well, you did find evidence. So isn't D? Oh, no, sorry. Wrong. E is the properly phrased one. You found the evidence you were looking for. That's what it means to reject the null. Researchers are interested in evaluating the effects of a natural product on reducing blood pressure. This will be done by comparing the mean reduction in blood pressure of a treatment natural product group and a placebo group using a two-sample t-test. The researchers would like to be able to detect whether the natural product reduces the pressure by at least 7 points more on average than the placebo. If the group size if groups of size 50 are used in the experiment, a two-sample t-test using a 0.01 significance level will have a power of 80% to detect a 7-point difference. All right. So remember, the power isn't the power the probability that you properly reject the null. So in this case, what they're looking for is they properly detect a difference of 7. If you are 7 different than the null, that is the probability that it will actually properly reject that null, okay? But let's say they want to be able to detect a 5-point difference, okay? So instead of a 7-point difference, they want to try to be detecting a 5-point difference. So let's think about that. Is that going to be easier or harder for the test to do? Harder. The closer it is to the null, won't it get more and more challenging for it to detect that there's actually a difference? Is everybody with me on that? The smaller difference you're looking for, the harder it's going to be to find, right? The further you are from the null, it's going to make it a whole lot easier to reject. So, what do we think? If it's getting harder to reject, harder for it to do its job, what is that going to do to the power? Won't that drop it? It won't be as strong, right? It would be less than 80. The test will not be able to do its job as efficiently. Oh, that'd be fun. So because the sample size is so small and it seems massive outlier, that's why we would be potentially hesitant. Oh yeah. It just isn't happening. Yeah.
After the AP test, you should like look up the experiments and then like create the exceptions.
There's a new Endgame trailer.
Is there? Can we watch it right now?
Yes.
Can you write me a past?
Yes.
Just
I would
say,
love
like,
to.
more important matters.
We had something to do. Yes.